Hi, everybody. I have your graded homework here. We can get that at the end of class. So I hope everyone saw the message with the newest problem set. It's now on the website with all of the other materials, so you can download it there if you to look at it again. All right. So let's see. Last time we started our discussion, very important discussion. It's really at the foundations of quantum mechanics itself. And that is thinking about what are called phase-space representations in quantum mechanics. So these representations are important because they help us to distinguish between classical and non-classical effects in physics. And what we seek to do is to answer the question, can we predict the probability of seeing a particular measurement outcome purely with a classical statistical theory? If we can, we say that phenomenon is classical. If we can't, we say it's non-classical. And one of the lessons that's important is that the answer to that question depends on what we're measuring. It's not just a property of the quantum state itself. It's also a property of the observable that's being measured. Okay? And this is not just a philosophical question, although that itself could be an interesting thing to address. It's also an important question from the notion of resources. If we think that non-classicality is a kind of resource for doing something, in processing information differently than we could based on classical physics, then this question of non-classical versus classical is a question of resources, okay? So, just to see why this makes a difference, as we were looking at different kinds of measurements we might do on light, we could think about direct photon counting, in which case the objects of interest are normally ordered products. And in the context of, say, squeezed light, we cannot predict everything we see from that kind of measurement using purely classical statistics, because the squeezed state can't be thought of as a statistical mixture of coherent states. So from that perspective, squeezed states are non-classical. But from the point of view of homodyne detection, what we saw is that the squeezed states were just Gaussian probability distributions that were purely classical. We can think about the measurement outcomes of homodyne detection from a classical statistical theory. Okay. So that's our motivation, and we are now developing the formalism to help us describe that. So the issue here has to do with the fact that in quantum mechanics we have non-compatible observables, observables that don't commute, which means we can't write down, generally, a joint probability distribution over the outcomes of non-commuting observables. If we could, then it would be equivalent to classical statistical mechanics, the Liouville equation for joint probability distributions on phase space. Okay? So because of the fact that X and P don't commute, or equivalently A and A dagger don't commute, we have to, how we write down a representation depends on what order we put X versus P or A versus A dagger. Okay? So Well, what we said is, okay, let us assume we have some observable, or it doesn't have to be observed, some operator, which is an operator on the Hilbert space, a infinite dimensional Hilbert space, say for a single mode of the electromagnetic field, or we can think about it as wave mechanics, okay? And we express that operator as a function of x and p, or equivalently as a function of a and a dagger, and we write a power series for that with some coefficients, with powers of a and a dagger, okay? And the coefficients here are labeled with a label sigma, because this depends on the order in which I write a and a dagger here. If we write them with all the a daggers on the left and all the a's on the right, we're going to say that sigma equals plus 1, for reasons that will become clearer, I hope, in a little bit. Okay? And that's the normal ordering of a and a dagger that we saw in Glauber's theory of photon count. When this index is -1, we write it in the what's called anti-normal order, where all the a daggers are on the right. Okay? And when this index is 0, we're going to call that symmetrically ordering, where we just look at all the permutations of this in a symmetric order. Okay? And importantly, this sum is the same for all these different orders, okay? These coefficients will be different coefficients for all those different orders, but the sum adds up to whatever operator we have. So there's different set of coefficients in this power series depending upon what ordering we're taking, okay? So we then define a function on phase space. So alpha here is a complex number. And we write it typically in our usual way, with the real imaginary part with that horrible square root of 2. So this is a function on phase space. Okay, so it's a function of x and p, or equivalently the complex amplitude x plus ip. All right, and that function is just what I get by taking this and setting a dagger to alpha star and a to alpha. Okay, at that point it doesn't matter. This is all the same, whatever order I am, because now they're numbers and they commute. And this is a different function for different values of sigma, because those coefficients are different. Okay, and so they represent what are sometimes called Weyl-ordered products. Hermann Weyl first wrote this down in the 30s, thinking about this problem in quantum mechanics. Okay. All right. So our goal is to write down these representations and figure out how to calculate them. Okay. Because we typically don't do this sort of brute force in this expansion, this power series. There's a trick to the trade. Okay, and you will all be tradesmen very soon. All right, so we have a lot of algebra to do. We have a number of little relations here that we started to talk about last time, reminding ourselves of what we call, the boson algebra, or the algebra of continuous variable quantum optics. I should, again, mention, this has almost nothing to do with quantum optics and everything, right? I mean, this is just quantum mechanics this describes the quantum mechanics of a particle moving in 1D, right? This is an infinite dimensional Hilbert space with wave functions. It would be exactly the same formalism, okay? And these questions we're asking about classical versus non-classical, they're fundamental questions of quantum mechanics itself. It's just that quantum optics, and I can say this, you know, as a arrogant quantum optician, is the only physicists who actually took quantum mechanics seriously in the last half of the 20th century and really wanted to understand, you know, we didn't want to shut up and calculate. And so all of these questions that were first visited in the 1920s and 1930s were revisited in the quantum optical context and sort of brought really back into the mainstream. Okay. All right. So with this algebra, we have, you know, the completeness relation for the coherent states. That allows, that's an important algebraic relation we use all the time. And importantly, in thinking about these operator-ordered products, a key algebraic object that we consider is the displacement operator. And once again, the displacement operator is defined as such, and when re-expressed in terms of x and p, it's kind of an operator plane wave. That's how I like to think about it. You see what I mean by that? It's an operator plane wave in phase space, because it has both an x and a p coordinate. And that gives us at least a hint that in the same way that plane waves are a complete basis of functions, i.e. the Fourier transform, we can always extend any function as a superposition of plane waves. It's the displacement operators form an operator basis, meaning I can take any operator A. We'll come back to any, when this converges or doesn't. I'm being somewhat sloppy, but we'll come back and maybe clean that up in a moment as to when this really is a good thing to do or not. But this is an operator basis, and I can take the operator A and project it onto the direction associated with this basis vector through the trace inner product. Okay? So this projects A onto that, and that gives me a coefficient, and then I can find the operator by adding up all the plane waves. So this is like an operator Fourier transform of sorts. Okay? Now, this is useful because it will allow us to instantly write down these operator-ordered products, because the displacement operator is the generator of such products. And let's see how. Let's look at the symmetric case. So if I take the displacement operator, let's say D for some complex amplitude beta, right? Oops, sorry. Well, now, if I just do a Taylor series expansion of this thing, then, all right, so I'll just quickly do that. then what you see is when I multiply those out, I get all the symmetric products of A and A dagger instantly. So this, in fact, is already a symmetrically ordered product. Because when I multiply out this using the binomial expansion there, I'm going to get all the possible permutations of A and A dagger for a given sum. So this itself is a symmetrically ordered product. Okay? Now using that, I can instantly see how, because if I take that expression, which I will in a moment, and plug it in here, you see that I already have an expression for the coefficients in the symmetric order, because I have these guys here. Okay? Now, it is the convention, let me rewrite this expansion over here. I'm going to write it in a slightly different way. So let's just say for the operator A is an integral over the phase space. Trace d dagger, of course, is equal to d of minus b. Okay. Just if I take the dagger, that just changes the complex amplitude to displace in the opposite direction. And now I'm just, because this is an integral over the whole phase space, I can integrate equally well over minus beta. So it's just the convention that we like to write this. And you know how much I pay attention to everybody else's convention, but this one makes sense. So I just made a substitution, beta goes to minus beta, and I integrate over the same thing. It's the same integral. Okay? Okay? So now I'm going to plug in this over here. And I'm going to get the sum over n and m, the integral over beta, minus beta to the m, plus beta star to the m, over n factorial, trace beta, d beta a, and then d dagger. You know, I already did the d dagger stuff. And then I have a dagger to the n, a to the n, symmetrically ordered. Okay? So all I did here was plug this into there where I set beta equals to minus beta. Okay. So here we are. We did it. These are the coefficients. Right? Because we just said that's how we're defining those coefficients, right? We define those coefficients just like that. So with this expansion, we get those coefficients. In this case, for sigma equals 0. Okay? So the symmetrically ordered expression for this operator is just what I get when I set A dagger to alpha star and A to alpha, right? But once I do that, I can resum over n and m. So, watch this. Watch this carefully. This is equal to okay. So all I did here is I said, as we said, we get the operator ordered representation by doing the power series and setting the A daggers to alpha stars and the A's to alpha. But in this case, I redo that sum and I get back the exponential that I had before, but now with A equals alpha and A dagger equals alpha star. So that is equal to the integral trace d A e to the minus beta alpha star plus beta star alpha, right? This guy is e to the minus beta A dagger plus beta star A. Okay, now that I skipped a couple of steps here because it's boring as hell. And you're just going to have to, if you don't follow all the steps, I don't care right now. You go back and you look at it. It's not so important this lecture that we see how all the algebra works. What I want you to think about is the concepts, okay? All right. So, with that said, we can now write this as the following thing. Okay, so let me explain what I've written down here. So I've defined a new operator, T, the symmetrically ordered guy, which is the integral over beta, e to the alpha beta star minus alpha star beta, the displacement operator. Okay, so what I did is I brought that integral into the trace, and when I do that, I get this. Okay, so the way that I calculate this symmetrically ordered representation is I take the trace of the operator with this operator T. Now, what the heck is this operator T? Anyone have a guess on what it is? What is this representing? Let me rewrite this in terms of the x and p components. Okay? So this is dx dp over 2 pi. There's a square root of 2 for each one of these guys. Let's call the beta, let's call those primes. Then I'll call alpha x plus ip over root 2 and beta x prime plus ip prime over root 2. So this then is equal to e to the minus I x p prime plus I p x prime e to the minus minus I. So this is equal to integral dx prime dp prime over 2 pi e to the I x p hat minus p plus I minus I p.
First exponential should be minus of that, right?
X minus x. This guy, I think that's right. I'll have to double check my algebra here. I'm integrating over x prime, right? Let me make sure I got this backwards. Oh, okay. Sorry. Okay. Doing algebra on the board is a mistake. I should look at my notes. Okay. This guy is beta, so that's a prime. That's a minus sign, that's a plus sign. Now it's right. Because this is e to the minus I x prime p minus p plus I p prime x minus x. Okay, that's now correct. Okay, so now I ask you folks, what is this operator T?
It's like a Fourier.
Go ahead, Stuart.
Like a Fourier transform in phase space.
It's a Fourier transform, okay? So let me ask you the following thing. Let's say this wasn't an operator. Let's say that was a number, p naught and x naught. What would this integral be? A delta function. That's what this is. And it's a delta function in this case, so this thing is equal to, it's two delta functions, 2 pi, a delta function, p minus p, x minus x, symmetrically ordered. So that's what this is doing. It's saying wherever you see the operator p, replace it by the number p. Wherever you see the operator x, replace it by the number x. You do that both for x and p, but you do it in a symmetric way. That is the symmetric representation in phase space. Okay? Let me show you an example of such a thing that you've seen before. Okay? Let's think about it for a second. Let's think about wave mechanics. Let's say I have a Hamiltonian. P squared over 2m plus v of x. That's an operator, right? This is the kinetic energy operator, this is the potential operator. Suppose I wanted to write a position representation of this operator. How would I do it? I would just make x equal to x, and that's the potential in the x representation. And if I wanted to write the kinetic energy operator in the momentum representation, what would it look like? It would just take the operator p and then replace it by the number p, okay? This, so I could, if I were to be super fancy, I could say this of x is the integral over x, v of x, with the delta function x minus x hat. And that just said for every I see x hat, say the value x, and that's a way to find a representation of this operator in position space. Now, what I'm doing is I'm finding a representation in both x and p at the same time. And I'm doing that through this crazy old operator, the symmetrically ordered delta function. And the symmetrically ordered delta function I can write as an integral of this exponent. Notice if x and p commuted, I could just separate this out. It's a delta function in p, it's a delta function in x, and everything is hunky and dory at the same time. But this, because they don't commute, I have to write it in this funny way. And that's a representation of the symmetrically ordered delta function. Okay. Now, when we deal with quantum optics, we often don't deal directly with x and p. We deal with a and a dagger instead. So let's revisit this integral over here. Let's substitute in here e to the beta a dagger minus beta star a. So this is equal to the integral e to the beta a dagger minus alpha star minus beta star a. Okay, that's the same thing as this, but now written in terms of the complex amplitudes and the a's and a daggers rather than the x's and p's. And this is, again, a symmetrically ordered delta function. So this is equal to pi, when you do all the delta function-y pi stuff. Delta function a dagger is equal to alpha star symmetrically ordered. Okay. So, we're going to see, as you will see in your homework, how you actually use these, what seem like absolutely crazy symbols. Okay, you put a 0 on there, symmetrically ordered. What the hell do you mean? Well, there are integrals and stuff we have to do, but conceptually, this is what we're doing. We're setting a dagger to alpha star and a dagger to alpha in a symmetric way, and that's this delta function is the manifestation of that, and we obtained it through this integral that we can do, as we will see. Okay. All right. Excellent. So, this, again, maybe I should just re-emphasize, this is the Fourier transform. Okay. Let me do a little aside over here. So I can think about a function. Now this is just a plain old function of two variables, x and p. Okay? And I want to Fourier transform this function. Usually we think about p as the conjugate to x, and I'm not doing that. Okay? I'm thinking about these are just two variables, just a function in a two-dimensional space, and I want to Fourier transform this two-dimensional function. So I'm going to define f tilde, and now these are the conjugate variables I'll call x prime and p prime. By Fourier transforming and I gotta look at my sign convention here because this is where I keep getting screwed up here. Doo-doo-doo-doo-doo. And the inverse Fourier transform with the other side. Okay, so this is all I'm doing here is I'm just Fourier transforming in 2D with a particular sign convention. Okay? X prime is the conjugate to X, and P prime is the conjugate to P. These kinds of Fourier transforms play an important role here in this whole business. Okay? Because if I think about this in terms of the complex variables, or the complex amplitudes, then f tilde of beta is the integral over alpha e to the beta alpha star minus beta star alpha, f of alpha, and f of alpha is the integral d beta alpha beta star minus alpha star beta f tilde beta. Okay? So this is a going back and forth where beta is the conjugate to alpha. Okay, I know this can be confusing, but it's just a Fourier transform in 2D. And that's what we've done. We did a Fourier transform over here in 2D. Fourier transformed the plane wave into a delta function. But in operator space. All right. Very good. All right, so, good. We'll come back to this. We know how, in principle, to calculate the symmetrically ordered representation of an operator. We'll come back to it. We can take this trace, or equivalently, we take this trace and we Fourier transform. What about the other orderings? Well, the displacement operator comes to our rescue once again. Okay. Let us recall that we know, using Baker-Campbell-Hausdorff, right, if we have e to the a plus b, this is equal to e to the a times e to the d times e to the minus 1/2, the commutator of a and b, if A and B commute with the commutator, so it truncates. Okay? So we have seen this many times now. That means I can write the displacement operator which is e to the alpha a dagger minus alpha star a, as e to the minus alpha squared e to the alpha a dagger e to the alpha star in the minus sign. Right? This, of course, is what we called in the past the normally ordered version of D. Notice this operator don't equal this operator. I gotta have this factor to make them equal. But here I have normally ordered things. Okay. So what this says, so I'm gonna call this thing D plus 1. That's to say I've normally ordered it. This is symmetrically ordered. This I will call D0. They're the same thing, because it's symmetrically ordered. Of course, this, if I chose the other thing, chose this to be A and that to be B, I would have gotten the following: e to the plus 1/2 alpha squared e to the minus alpha star A e to the alpha a dagger. That comes from just doing Baker-Campbell-Hausdorff again, but calling this thing A and this thing B, and just commuting in the other order. Okay. So this is the anti-normally ordered version of D. This is D minus 1. D minus 1 and D plus 1 do not equal D0. You have to put in the right exponent here. But I can define generally D sigma is defined to be e to the sigma over 2 alpha squared d alpha. Does that work? When I write D plus 1, and I would have, that means that D plus 1 of alpha is e to the plus 1/2 alpha squared d. But if I plug that in, I get yay! So that, in fact, is true, right? Because if I multiply this by plus 1/2, I can cancel that, and I get that off. Okay. Similarly, D minus 1 is this, right? Because when I multiply it by minus 1/2, I can cancel that, and I get that. Yay! So, this tells us I can write the sigma ordered product in terms of this guy through that factor. And in fact, I can think about this as an analytic function. Now I think of sigma as a continuous variable between 0 and 1. If I wanted to, we could define a kind of, or just define it that way. Although we only ever really think about the three cases, minus 1, plus 1, and 0. Yeah?
Wouldn't it go minus 1 too?
Yeah, it would. It would. That's exactly what it would do. Thanks. Okay, so let's think about this now. So if I look at, let's look at D plus 1. that's equal to that. Right? That's the normally ordered guy. But I can now take each one of these guys and write it as a power series and multiply them together. And what I then get is the sum over n and m goes from 0 to infinity, alpha to the n minus alpha star to the m over n factorial over m factorial, a dagger to the n, a to the m. Which is the normally ordered product of a and a dagger. As opposed to over here, when we expanded the D, we didn't get the normally ordered guy, we got the symmetrically ordered guy. Okay? It's the same kind of coefficients, but just this guy is normally ordered. Okay? Notice these two operators are not equal. Right? Because a and a dagger don't commute. Similarly, and when I expand each of these in a power series, I'll call this power series over the index m, and this power series over the index n, because I can, because they're dummies. Not saying you guys are saying those indices are. I get it. No, actually, I'm the dummy. I should have done it this way. Yeah, call that n, call that n. This is n. So, what we see here, thus, is that the d sub sigma, as defined over there, is equal to the sigma ordered power series. When sigma was 0, that's what we got over there. When sigma is plus 1, we get the normally ordered guy. When sigma is minus 1, we get the anti-normally ordered guy. Okay? Yes?
What happened to the minus sign?
I forgot about it. Thank you for keeping me vaguely honest. It's important to not get lost. Okay? So now what? Now, there's a few more tricks up my sleeve. I'm trying to keep rolling them up to show you that there's nothing up there. I know this is hairy, but we'll just keep going. Raising the board gave us a nice breather. Let us continue. All right, so what we had written, look at this expression over here. Let's revisit this expression over here. So, come on, board. Stay with me. A, I'm just going to rewrite it again, is the integral over phase space with some dummy in X, the trace of A with d beta times d beta minus. Right? I just rewrote that expression that's sitting over here. Okay? All right. So what we want, though, is the sigma ordered d here. Because when we have the symmetrically ordered d, we got the symmetrically ordered representation. We want the arbitrary sigma ordered d. And the arbitrary sigma ordered d is defined this way. So anybody have a suggestion of how we're going to get there?
Plug it in.
So, sort of. I mean, what are we going to plug in? I mean, this is an equality, so what do we plug in? Well, you can solve for d and put in the solve it on the other side, right? Another way of saying that is I'm going to multiply this by e to the plus sigma beta squared over 2, and this by minus sigma beta squared over 2. Right? I could do that. Or the other way around. I'll put this guy, doesn't really matter. I'll do it like that. Okay. This is 1. It's a number. Right? So, what do I have? This is equal to the integral over beta trace A with d minus sigma of beta trace, times d of sigma, d sub sigma of minus beta. So that's a general expression. When sigma was 0, we had the original one. When sigma is plus or minus 1, we have that. And there we have it. Because now this, because I'm such a good professor, I had this right above. First time in history. And all we have to do, we plug that back in, and then we substitute A dag is alpha squared, and A is alpha. And we redo the sum, and we get the exponential again. So, what we have, thus, is that the sigma ordered, file ordered, is equal to the same thing we had Now I've done it. It's the sigma ordered product. Sorry about the pens. I'm going to try one of the green ones. That seems better. Okay, so let us summarize here what we have in the green. If I want to obtain the sigma ordered Weyl symbol, the representation for sigma ordering, what I need to do is project A onto the minus sigma. Now this is where I differ from other conventions. This minus sign, this is the way it's always this duality. It's important to understand. We'll see why this duality matters. Plus and minus. It's a yin and a yang. Okay, what is this symbol? T minus, or T for some sigma of alpha is defined to be the Fourier transform of the sigma ordered displacement operator. So we had over here, right? This was for the symmetric case. This was for the symmetric case, and we had the symmetrically ordered delta function. Now we have the sigma ordered delta function. Let's do an example. Let's say that sigma is +1. So T of +1 of alpha is equal to the normally ordered guy right? Over beta.
That would also change in the box as well, right?
Thank you very much. Thank you. Okay, so this is equal to the integral over the phase space, e to the beta a dagger minus alpha star, e to the beta star, a minus alpha. But what is that? That's the normally ordered delta function, right? Because everything here is separated from this. I can do these integrals separately. And this is equal to pi sigma, delta function a dagger minus alpha star. So this is the normally ordered delta function, where all the a daggers are on the left and all the a's are on the right. As opposed to T0, where I could never write it down, and only can write it down as an integral. And what's your guess for the -1 case? I just flip it, right? Then it's going to be the anti-normally ordered delta function. All right, so we now have at least a formal solution for how to find the sigma ordered representation. I take this trace. I have to do it, if I want the normally ordered guy, I have to trace with the anti-normally ordered T. If I want the anti-normally ordered product here, I have to trace with the normally ordered T. Symmetric, symmetric. They go in this dual way. That's going to be important, as we will see, when we finally get to physics at some point. Okay. All right. So, of particular interest to us is the density operator. That's a particularly important operator because that is what determines the state of the system. And we want representations of the density operator. Okay? So, the way it's defined, we define these things and call them W sub sigma, is just equal to the, it's going to just have a factor of normalization, rho. So this is going to be equal to the integral 1 over pi, the trace of t minus sigma of alpha with rho. Okay. Or, if you like, 1 over d beta pi squared e to the alpha beta star minus alpha star beta, the trace of rho with d minus sigma. So this is the sigma-ordered representation of rho. They have names. When sigma equals 0, we call this the Wigner function. And we usually just call it W of alpha or W of x and p, although there's factors of 2 in their normalization because of the stupid square roots of 2's in there. When sigma equals plus 1, that's the normally ordered representation. We call this the Husini function. And we typically call it, in quantum optics, Q. When sigma equals minus 1, it's our friend we have seen before. It's the Glauber, Sudarshan P representation. And guess what we call it? P. Okay. So these are, as we motivated earlier in the last lecture, there are different ways that people thought about phase-space representations, but they were later understood to be just different operator orderings that will have physical significance. Okay? So the Wigner function was written down in the 30s by Wigner. God knows when Husini wrote this down, probably in the 1940s, I don't know. And Glauber did this, well, with Sudarshan at the same time. Sudarshan did it separately in the early 1960s. They all seem to be different representations. And what we're going to see is they have different physical implications. How would you calculate it? Well, typically, this is how you calculate it. You have to take the trace of rho with the displacement operator and then inverse Fourier transform. That's the way it's typically done, as you will see in your homework. Yeah?
Can you clarify, are these different states then, or?
No. They're different representations. Like you remember from your elementary quantum mechanics, I can have the position representation or the momentum representation of the same state. So if I have a free particle eigenstate in momentum representation, it's a plane wave. In position representation, it's a plane wave. In momentum representation, it's a delta function. If I have a position eigenstate, in position representation, it's a delta function. In momentum representation, it's a plane wave. So these are, it's one and only one state. But these are different representations.
How could that have physical differences between the different representations? It's got to have the same measurement outcomes, right?
So we need to wait a moment. They, of course, in principle, any representation can be used to describe any measurement we can do, but some representations are more useful than others. So for example, if I'm measuring momentum, it's convenient to work in the momentum representation. If I'm measuring position, it's convenient to measure in the position representation. Now these are neither momentum nor position representations. They're both at the same time. They're both position and momentum representations at the same time. They're phase space representations, and these different functions will have different usefulness with respect to different measurements, as we have already seen. When thinking about direct photon detection, the P representation has a natural interpretation. As we will see, for homodyne detection, the Wigner function does. Okay. So we'll see this in a little bit. Thank you for these good and clarifying questions. I appreciate it. All right. So maybe to begin to push a little bit in this direction, how is this going to be related to things like measurement? Well, often we're thinking about, expectation values or correlation functions, right? So what I'm really interested in is I might say, might tell me something like, what is the expected value of some observable? That, of course, is equal to the trace of A with rho. And we want to write this as a phase space integral. Okay? How are we going to do that? Well, to do that, we're going to we have the last trick that we're going to pull from our sleeve here, which is that the delta functions are also a complete basis of operators in the same way that the displacement operators were. They're just the Fourier transform. So any operator A can be expressed this expression is just the same as this expression. We said that the plane waves represented an orthonormal basis. If I Fourier transform it, I get the delta functions. Okay. This is that, right? So, what we see, if I then take the trace of this with this, I get this is equal to the integral over all space, the trace of rho with t minus sigma. But this is the sigma ordered function. So let me just box this, explain it, and we'll conclude, I think, here. So, what do we see here? It says, if I want to calculate the expected value of this observable, I can think about it as a phase space integral. I integrate over all of phase space with this function, but I have to do this duality. If I want to look at sigma ordered here, I have to look at minus sigma ordered for the state. They come in a dual pair. Why is this useful and why is this interesting? Let me come to a different board. Let's just think about classical mechanics, statistical mechanics. Let's say, how would I describe the state of the system? Well, if I know for sure it's a point in phase space. But if I just have classical statistics, I would say I have some probability distribution on phase space. I could, if I wanted to, I could write down the Liouville theory, which tells me how the thing evolves in phase space. It evolved according to a Poisson bracket. Right? And if I wanted to look at some observable, which is on phase space, and I wanted to know what its mean value was, I would take this and I'd integrate it over the probability distribution. What we have attempted to do here with all our fancy operator algebra is to re-express quantum mechanics as close as we can to classical mechanics. This object is my state, and we call it a quasi-probability distribution. On phase space. This quantum mechanical expression is exactly the analog of this, where we have an operator that is a function on phase space and a state which is a quasi-probability distribution of phase space. If it was an actual probability distribution of phase space, well then this would be classical mechanics. And we would say that this was a classical phenomenon. But as we will see, for some quantum states, this is not a probability distribution, meaning it can be negative. And probability distributions have to be positive. That's a really profound thing. And in my opinion, maybe, just maybe the most profound thing. And maybe the whole answer to what the hell quantum mechanics means itself. How it differs from classical mechanics. Okay. So we're going to come back now and look at all these things more carefully. Of course, we have, and this goes back to your question, Matt. Obviously, I can use any representation I like, but they're going to be more convenient representations. Okay? And so we will see that the choice of representation will be more convenient or not for particular measurements, although this is an equality for any of these representations. Very good. All right, I'll take some questions offline here and we'll just call it quits for now.